Thank you for introduction. I'm very glad to talk about my recent study. Thanks a lot to the organizers and everyone. Today, I'm talking about divalent cation blocking mechanisms in prokaryotic sodium channel. At first, briefly, I'd like to introduce me. I'm Katsumasa Irie. Please call me Kaz. I came from Wakayama Medical University. Wakayama is located near to Kyoto and Osaka. So it is viewing from my laboratory. So Wakayama also has very lot of good food and to historical place and good culture. And Wakayama is best access to Kansai Airport. So don't you forget to visit Wakayama when you came to Japan. So this is one of the best place of Wakayama. It's called Kumano-Kodo. It is World Heritage. This is the ancient path for pilgrimage connected this line. So this place is very, very wonderful, and we can enjoy the history and the nature of Japan. In this study, I'm using prokaryotic cation channels for molecular analysis. Prokaryotic channels are ancient paths for ions in all of lives. So I'd like to talk about the latest finding, the molecular mechanisms of divalent cations obtained from these channels. Divalent cation blocking is observed in various tetrameric channels. Especially, most famous one is observed in NMDA receptor. NMDA receptor is activated by a neurotransmitter in postsynapse. But without depolarization, magnesium ion block this current. Under the depolarization condition, magnesium ions was released, and this receptor can generate the current. So this magnesium ion block is included in the various important phenomena such as memory formation. But the detailed molecular mechanisms still unknown because these magnesium ions have not been directly observed. On the other hand, as I said, prokaryotic channels are my favorite proteins, and recently we found one of them shows the divalent cation blocking properties. And also, we found the prokaryotic calcium channel named CAV-MR. Calcium channels are thought to be evolutionarily close to ancestral channel. So this channel group we named ancestor-like back nerve, shortly said uncle nerve. So and this NABPP is also belong to uncle nerve groups, and it shows calcium. This current was blocked by calcium ion. So it is very interesting that uncle nerve shows similar property to NMDA receptor. And as you know, NABAB is most structure studied prokaryotic channels, and it did not show calcium ion blocking. So if NABAB obtained divalent cation blocking properties, we can analyze the detailed mechanisms of divalent cation blocking. So we did the mutational analysis, and we can obtain the NABAB mutants showing divalent cation blocking. So I would like to talk about three topics. The first, the generation of the divalent cation blocking mutant of NABAB. And next, crystallographic structure analysis of these mutants, and we can find the binding position of divalent cations. And we propose the blocking mechanisms hypothesis. And at last, a molecular dynamics study to evaluate the blocking hypothesis. Let's start. In NMDA receptors, this aspartate residue is concerned with magnesium blocking. Overlapping this 4-domain to NABAB, we can find NABAB's leucine 176 is corresponding this asparagine. So this mutation is first candidate. And second candidate, we choose this mutant. This is AMPA receptor. It is similar to NMDA receptor. So in AMPA receptor, glutamine residues corresponding these leucine residue. These residues. So all electrophysiologic data were obtained by a whole cell patch clamp method of insect cell. And this mutation, N49K, is introduced all channels in this study for the easy measurement. In the wild-type channel, NABAB did not show calcium blocking by the various extracellular calcium ion. But these two mutants showed calcium blocking, current was blocked by extracellular calcium ions. So we evaluate blocking rate by this tail current. In the wild type, current was not reduced at any calcium ion condition. So it indicates a blocking rate. In these two mutants, the current was reduced to 20% under the 40 millimolar calcium ion concentration. So these mutants showed current was blocked by calcium ion. So next, we evaluate the effect of other divalent cations such as magnesium ion and strontium ion. So these divalent cation also showing blocking effect. So this blocking was caused by divalent cations commonly. Next, we did similar measurement with other mutant. This threonine mutant is similar to these mutants because it is a hydrophilic mutation. This hydrophilic mutation also shows a blocking effect by calcium. And such as alanine or glycine, it is a small side chain mutant. They show also a calcium blocking effect. But such as phenylalanine, it is a large side chain mutation, but this mutation did not show a calcium blocking effect. So we try to crystallize these blocking mutants, and we can obtain these two mutant structures and a wild-type structure under a calcium-free condition and calcium condition. So this glutamate mutant represents hydrophilic mutant structure, and this glycine mutant structure represents small side chain mutant structure. And worst resolution of this structure is 3.5 angstrom. So in following study, we compared the electron densities at this resolution. This is the electron density in the selectivity filter and ion pathway. It is a selectivity filter, and this is an ion pathway. So under calcium-free conditions and calcium condition. So there are three ion interaction sites named site HFS and site center and site in. Site center is defined by leucine 176 carbonyl group oxygen. So we defined as zero origin of z-axis. And site in is defined by threonine 175 oxygen. So it is correspond -5 angstrom position of z-axis. So ion and waters interact with these sites. sorry. To compare the electron density, we drawn this orange mesh. This orange mesh is the electron density, the calcium ion condition subtracted with calcium-free condition. So this orange mesh can enhance the position of calcium ion. But in this wild-type channel, we can observe the orange mesh rarely in ion pathway. And in case of glutamate mutant, we can observe the clear orange mesh around the site center and site in. So it indicates calcium bind these sites tightly. Next, we compare the electron density between the glutamate mutant and wild type. So this brown mesh is the electron density of mutant electron density subtracted by wild type density. So it can emphasize the difference of effect of mutational effect. So we can see the brown mesh around the site in the calcium-free condition and calcium condition. So by the glutamate mutation, site in's hydrophilicity up, so ion or waters was trapped around here. So and calcium ion conditions, this density is increased, and it is corresponds to calcium ion. This is a glycine mutant electron density. In the case of the glycine mutant, we can also observe the brown mesh around the site in. So these glycine mutations makes the additional group around here. So water or ions can entrance here. So these water can trap the calcium around here, around this position. This position. From this structure, we hypothesize the model of divalent cation blocking. In the hydrophilic mutant, calcium ion can bind the bottom of selectivity filter by the hydrophilic mutation. So this calcium inhibits the entrance of natrium ions. And also, these small side chain mutants, the extra cavity, in the extra cavities, water can enter here, and this water traps calcium and similarly inhibits sodium current. So, to evaluate this hypothesis, we try to the molecular dynamic simulations. Molecular dynamic simulations were done with Dr. Sumikama of Kanazawa University. And for large-scale calculation, we used the supercomputer of the National Institute Natural Science. And we applied electronic continuum correction method, applied this method to optimize the charge and radius parameter of ions. This is this is 10 nanosecond movies. We can see the permeating of sodium ions here. And this green, yellow ball is sodium ions. We can see sodium ion permeation here. But movie did not move now. Sorry. So this is the trajectory of the sodium ions for 100 nanosecond simulation. So each line indicates ion's trajectory. So we can see the sodium ion come from the extracellular side and get in the selectivity filter and channel lumen, and finally get into the cytosolic side. So we can see the sodium ion permeations in the calcium-free condition and calcium condition. In this case, rarely permeate calcium ions, so it is correspond to permeation ratio of calcium of this channel. So this simulation will represent real situations. And it is a trajectory of the blocking mutant. It is a calcium-free condition and calcium condition. We can see the sodium ion permeation occurred in the calcium-free condition, but in the calcium condition, partially sodium ion permeating is completely blocked. In this time, calcium ions stay in the channel lumen. So when calcium ions stay in the channel lumen, sodium ions permeation is completely blocked, such as here, and such as here. So from this trajectory, we calculate the current of channel in the simulations. This left bar indicates the current of calcium-free conditions, and right bar indicates the current of calcium condition. Its painted part is the sodium ion current, and this white part is calcium ion current. This current value is well correspond to the single channel recordings of real experiment. And these blocking mutants current were decreased under the calcium ion condition. So these results, these simulations represent the real situations. So we investigate the detailed state of ions under each condition. So we evaluate the free energy of each ion. The z-axis is horizontal axis, and a vertical axis is radius of ion pathway. These parameters corresponding here. Z is here, and radius is here. So blue part is low free energy region, and so in this position, ions are locating stably. And red part is high energy part, so it is rarely stays ions, and this white part is there are no ions. This graph is corresponding to this structure. So, to simplify, we accumulate this region. It is 10 angstrom radius region and plotted to one-dimensional graph. This part accumulate to this graph. This black solid line indicates calcium-free conditions, sodium ions free energy. And red solid line indicates under the calcium conditions, sodium ions free energy. The red dashed line is calcium ions free energy. At first, we compare the wild type to hydrophilic mutants free energy. So we can see the calcium ions free energy is very low, around Z equals 0 to -5 angstrom position. This position is correspond to crystal structure. So, and this position is corresponding the site in position. So it is well explains crystallographic data, and these data enforce the blocking mechanism each other. So this lower calcium free energy, so in these mutants, sodium energy get around the intracellular gate, free energy getting higher. So in the case of these mutants, sodium ions cannot permeate the channel, this channel. And it is a small size mutant, but in this case, we cannot see the lower part of calcium ion free energy part. But sodium ions free energy is getting higher around the intracellular gate. So we evaluate the water's density around the mutational site. it is indicates the density of water. A blue part is low concentration of water, and red part is high concentration water. In this red circle, the mutational around the mutational position, and we can see the increment of waters in these small side chain mutants, such as here, but in wild type not here. And this is a snapshot of MD simulation around this mutational site. And we can see the additional waters around this small side chain. So in these small side chain mutants, these waters stabilize these calcium ions. So here is a summary of my presentation. These hydrophilic mutation creates a binding position of calcium around the bottom of the selectivity filter and block the current. And also, small side chain mutants, additional water can stabilize calcium and block the sodium current. So in this study, we propose the basic molecular mechanisms for divalent cation blocking. By applying this system to NMD receptor, it's also possible to analyze the mechanism of current blocking by magnesium ions of NMDA receptor. That is all my presentation. This research was proceeded with these collaborations. Thank you for your attention.